everyone, and welcome to today's webinar on transformer oil testing. Today, we're thrilled to have each of you here as we delve into this critical topic, covering the essential role of transformer oil testing and electrical system maintenance and reliability. This webinar is proudly presented by ALS, where we're committed to advancing your knowledge on crucial maintenance practices and ensuring the health of your assets. Today, we're joined by Stephen Durand, an expert in transformer diagnostics with years of hands-on experience in this field. Stephen brings a wealth of knowledge in transformer health assessment, condition monitoring, and failure analysis, and he's here to share valuable insights on how regular oil testing can help you enhance equipment reliability and avoid costly unplanned outages. A few notes on using Zoom webinars. Throughout the presentation, we invite you to submit any questions that come up using the chat feature. Simply type your question and we'll be collecting them as we go along. There will be a Q&A session at the end of the webinar where Stephen will address as many of your questions as time allows. If we don't get to your question during the live session, please know that we'll follow up individually to ensure that each of you receive the answers you need. Thank you again for joining us, and without further ado, let's welcome Stephen Durand. Stephen, over to you.
Good afternoon. My name is Steve Durand. I've been within the transformer fluid testing industry for approximately 20 years. We're going to discuss today the test methods and the diagnostics test results and how they work within the field. It's to detect contaminants within the oil, not just the oil, but also if we do have contaminants within the paper insulation. So best way to say it is the oil, it acts as an insulator to the flow of electricity, and there is paper wrapped around all the windings, all the copper in there to prevent electricity flow that way. So it identifies moisture, dirt, particles that degrade oil quality. We also do monitors oil condition to ensure it's doing what it's supposed to do, just like the insulating and cooling properties over time. Identifies gas byproducts that, as you can detects gases indicating internal faults. We also use it to track trends and prevent failures by identifying problems early. So one of the reasons why we try and have a quick turnaround time is for that reason. Most effective, cost-effective maintenance. If you can find the problem before it actually becomes a big problem, it's much easier to repair and ensures compliance, meets industry standards for safety and performance, especially when it comes to any company that has a transformer on site. They will not get their insurance unless they pass all the transformer testing. And that's not just oil, but also electric testing. So here's the basics on transformers. As you can see in this little diagram, it's basically pulled out of your science textbooks from like grade 10, I believe. For Canadians, it's grade 10. I believe it's sophomores down in the States. Transformers operate by providing using a coil of conductive material, usually copper, which is wrapped around a steel metal core, which is usually steel. A second coil is wrapped around the same core with no contact to the first coil. What this does is it causes the electrons to flow from one coil to the other using electromagnetic radiation, electromagnetic field, to cause it to excite the electrons in the other coil. So the primary supply, it depends on the number of turns on the way in and the way out. So the more turns on one side, so if you have more turns on the primary and less on the secondary, it'll drop the voltage. If you have more on the secondary than the primary, it'll raise the voltage. The reason why we do this instead of using direct current is because with alternating current, you can transmit it thousands of kilometers away, versus you would almost have to live, 5 kilometers away from every power plant if we use direct current. That's the reason why we do this. So these are basically the most widely used transformers are for distribution of electricity to homes and businesses, which allow the power from the generating plants to be used safely by people. So everyone's seen the green boxes in their neighborhoods, the little pole tops on top of poles, essentially, and the one in the middle is your slightly larger one. These are the smaller ones that we tend to call them kind of throwaways because they tend not to test this so much. It's more in the ones that are distributing even farther, like from you have large power going into a transformer and then we're bringing it out. Usually you've seen these stations throughout every city. The reason why we test is because this can happen. A big explosion like that's quite normal. Transformer failures can occur for a variety of reasons, resulting in inconveniences such as power disruption to millions of dollars in damages and or death. As you can obviously see, regular schedule transformer fluid testing provides personnel safety and prevents environmental mishaps and component failure, ensures transformer reliability and uninterrupted operation, and optimizes maintenance practices while reducing costs. Explosions like this are fairly rare, but they do happen, and it's a lot of times it's from not maintaining and not inspecting transformers. Our focus today is on insulating liquid-filled transformers. The insulating fluid is used to cool the windings and acts as an insulation. We have several different types of oils that we test. We have mineral oils, which is the most common. It's fairly cheap in comparability, and but the biggest problem is it does have an environmental impact if there is a spill. You would need to remediate the area, dig up anything that's got contaminated from your mineral oils. Synthetic oils are synthesized from natural gas. So this would be ones that are called triluminol. They're more costly than mineral oil, but safer due to a higher flash point, indicating that they can heat up more before they actually flash over. Now, natural and synthetic esters are created from vegetable oils, often from soybeans. They're safer than oils due to the higher flash point, environmentally safer, as it can biodegrade when spillage happens. Also, the main part about these is because they are esters, they do have the ability to hold more moisture within it. And we'll get into that a little further. There are also discontinued insulating fluids where they can show up, but they tend not to. These include RTEMP, which is a replacement PCB fluid because it's thicker and it has a similar viscosity to PCB fluids. So it was developed to be able to run within a remediated transformer, which will have because the viscosity difference between that and mineral oil, you couldn't put mineral oil into a PCB fluid transformer for that reason. It doesn't work in the same way. Silicone fluids were a replacement for PCB fluid and often used in indoor transformers because of its higher flash point as well. PCB fluids have been banned since the 1970s due to the environmental persistence and being a cause of some cancers, but they have great dielectric properties. There's a reason why they use them. Very seldom was there problems in terms of the electrical portions. And then perchloroethylene was used as a remediation. So what they would do is they drain out the PCB fluid, they would add in the perchloroethylene and let that circulate. Just run the transformer for another year, go in, take that perchloroethylene out, put new perchloroethylene in, and that would drop the PCB rates. Now, any PCB or perchloroethylene samples received for testing will be rejected due to contamination concerns for equipment. There is no way on testing it. And you can definitely tell because the PCB and perchloroethylene is twice as heavy as mineral oil. It's very noticeable. These are our sampling kits. There are many different tests that can be performed. So we use a 1 liter plastic bottle and a 50 ml reusable glass syringe. This glass syringe has, I don't think I have it here, but it has a serial number on the piston and the barrel, meaning that they've been matched to make sure it's airtight. We reuse these because they're expensive, and we just clean them. The bottles, 1 use only, and with 1 liter, we can get all the tests that we need to perform in that. Okay, and this is what they look like when they're full. Each sample container must be filled as below. It needs to be so in the bottle, bring it to the bottom of the neck. So you can actually have a little bit of thermal expansion of the liquid. So if you're taking the sample when it's cold and you bring it into a room, if you fill it all the way up to the top, there's a possibility that the thermal expansion can actually pop the lid off. I have seen that. It's not fun to go clean up. And syringe must not be filled past the 50 mil mark, because air can start leaking if you're I don't know if you can see my cursor, if you're too far back, and that will actually cause a problem. Now let's start talking about the testing. During production of electrical insulating fluids, many tests are performed to verify the properties of the fluids. Many of the tests are the same tests that are used for lubricating fluids, such as viscosity, flash point, fire point, and we actually have gassing tendency. These are generally only tested for in the initial sale of fluids. So once we've found out that it matches what it needs to match, we tend not to use that as our regular testing. Other test methods are performed on an ongoing basis to ensure the properties are within the acceptable ranges as set by the governing bodies like the Institute of Electrical and Electronics Engineers, that's IEEE, and the International Electrotechnical Commission, IEC. That can be broken down into the following categories: chemical tests, electrical tests, and physical tests. The routine chemical tests are dissolved gas analysis, polychlorinated biphenyls, or PCBs, corrosive sulfur, neutralization number, or TAN, oxidation inhibitor, moisture, gerons. We also do color, interfacial tension, density, visual examination, and then the electrical ones are dielectric breakdown and dissipation factor. Let's talk about dielectric breakdown. It tests the ability of the electrical insulating fluid to withstand an electrical charge. This is the most important test because this is what the fluid's meant to do. So any part within the transformer that has cabling or any sort of metal needs to be wrapped in paper or surrounded by oil. So when we have connections, it's just oil. The idea of the oil is to prevent any electricity flow from going from one part to another metal part. Excuse me. It's sensitive to suspended particles in the oil. So if you have particles, if you sampled it poorly and there's stuff from the sample valve, that'll cause this to be poor. So this is measured in kilovolts. So it initially starts testing at 5 kilovolts or 5,000 volts and goes up. Anything lower than that, it is not good. It's not going to work. Interfacial tension is a test for the presence of polar contaminants within the oil, including acidic compounds, water, and paper compounds. The amount of force required to pull, so it's measured in force. This does not apply to silicone and ester fluids because they are polar in nature and they can hold in water really well. So those tests are always significantly lower. TAN, total acid number. It's a coulometric test and it checks for acidic compounds that can damage the paper. So if your acid amount gets higher and higher, it can create sludging, and that can actually get onto the paper and eat through it. The paper is the main insulation medium, and we need to protect that at all costs, or else that transformer now just becomes a very big circuit, and it's going to cause tons of arcing and cause lots of damage. Relative density, or specific gravity. It's basically telling you how much that fluid weighs. So you can use the volume, multiply it by your density to get an idea of what the weight is if you need to go and add something in. So you get a weight mass by mass, which is a much better way of doing it than volume based, or if you need to transport the fluid. So if you're draining it out and you need to make sure that you can fill up your tanker and not have it cause problems in terms of, it gets too heavy and you end up going in the wrong way of doing things, and you might need another tanker in order to be able to handle it. Color and visual inspection. So the color is just a check to make sure it gives you an idea of the age of the transformer and if the resin's been leaking out in the same way. So how that works is um, when it comes to press board versus just regular wrapping of paper, they need to put a resin in it to keep it rigid, and the resin will slowly leak into the oil, usually over like 30-40 years. It'll start getting darker and darker. Now, the visual inspection is the most important one that we do in terms of whether we should test this or not. It detects whether the sample has been taken properly. So the idea being, when you go and take the sample, you take out the plug from the port, you clean that out because most transformers are outside. It's going to get dirt and grime, and then you flush. You flush through usually 2-3 liters before you even take your sample. And once you take your sample, you check for clarity, sediments, and free water. This should be done in the field. If we get stuff that has free water in it or it's really cloudy, we can't test it electrically because it's going to fail regardless. The best thing to do is to reject the sample and ask them to resample. I've seen samples from people who've been doing this for 30 years come in and it's still bad from the actual sample because they're like, I drained out 10 liters. Because the water can get into the transformer if there is a leak near the top. Moisture. Everyone knows what moisture content is. Test for the presence of water dissolved in the fluid using the Karl-Fischer titration method. Water in the oil can cause damage to the paper insulation. It can also form water droplets in the oil, which can cause electricity to flow where there should not be. Now, the good thing with the ester fluids is we don't need to worry so much about moisture because ester fluids have there's an ester, so there is open oxygen bonds. It can actually suck in the water. So water content for oil no higher than 35. Water content for in-service ester fluids 400 ppm. Gives you an idea. Now, dissipation factor is another electrical test. This test measures the AC losses of the electrical insulation fluid. It's dependent on temperature. So most time, if you're doing in service, like if in use transformers, you do 25 degrees, and then they'll do 100 degrees Celsius for the test, or 212 Fahrenheit, just to make sure it's operating the way it should. You should never run a transformer above, like the core temperature should never get above 40. Every 3 degrees above the recommended operating temperature will actually decrease the life of the transformer by half. So it's best to try and make sure that you run it the way it should be. And this is also very sensitive particulates in fluid. Dissolved gas analysis. This is the most important test for the condition of the internal parts. So all the other ones were, is the oil doing what it's supposed to do? This one is what's happening inside. This is what we refer to as the blood test of the transformer. We use it to detect electrical faults, oil degradation, or overheating faults. We can also use this to give us an idea of, do we need to check the paper insulation? Gases can form from internal faults or are environmental in origin. So we also look at oxygen and nitrogen. That'll give us an idea of, do we have a leak in this unit, or have they opened it up when the oxygen level jumps, or even if they took the sample poorly. PCB determination. This tests for the presence of PCB compounds within the fluid. The presence of PCBs in other fluids is due to either intentional additions made by manufacturers until the 1970s to improve the performance of mineral oil, because PCBs have great dielectric properties. I've never seen it below 75. And unintentional additions from cross-contamination. Before they understood what cross-contamination was, like you have to drain down a PCB-filled transformer to replace some gaskets because they're starting to leak and pump it back in. Then you go to the next one, you don't flush, you don't clean out, and that's just cross-contamination. Furanic compounds. This tests for the presence of furanic compounds, which is an indirect measure of the condition of the paper insulation. These are intermediate products from the breakdown of paper. So how that works is, as it's heated within an oily medium, without oxygen, these furan compounds will be formed and slowly degrade into sugar. So basically a sweet sugary compound. So if you smell sweet on the sample, it's probably not doing so well. Generally, paper will always release these things, but they'll break down at the same rate that they're being generated, so we'll keep it low. As they go up, it indicates that the paper is being heated faster than it should. It's going to be more heating. That could either be from you're running it too hot or your radiator fins are plugged up with garbage, which I've heard about and seen. Oxidation inhibitors. These are compounds that we put in to prevent the oxidation of the insulating fluid. This will help us with making sure that the acid level doesn't go up. So if the tan is increasing, then we generally want to see what's our oxidative inhibitor levels, and we can actually add on to it, add these things later, usually weight by weight using specific routing. So interpretations. In North America, ASTM test methods are used almost exclusively. In Europe, they prefer the IC methods. These methods, they come up with the same results, but the values are going to be slightly different because the methods are slightly different. For dielectric testing, our dielectric tester allows us to do both the IEC and the ASTM methods, whatever they're, and even some of the Australian and British methods. For interpretation of the data received from ASTM tests, the IEEE developed testing limits for each test that corresponds to the equipment being tested. ALS uses the IEEE guides to provide these interpretations. Unlike in other oil testing, we do all of our testing based off IEEE versus the manufacturer's original requirements, because that's just how we need to do things. Okay, and I think that's the end of my slides. Yep, completely done. All right. Does anybody have any questions?
Okay, thanks, Stephen. Let me move on to the Q&A. Okay. We have a few questions. Let me see. Let's get one for you. Okay, question 1 is, how has ALS optimized their process, cutting traditional turnaround times in half?
That's a really good question. Generally in the transformer oil industry, turnaround times are 2 weeks to 6 weeks for results. We've cut it in half literally by running it very similar to a oils and lubricants lab, which has a 48-hour turnaround time. We do our turnaround time within 7 days or 5 business days, because that's just how we operate. Some of our competitors have been known to have like 6 weeks. The reason why we do that is because my previous place I worked in the transformer oil industry, they also did sampling and testing of transformers themselves, like testing up the electrical side. And I would see time and time again reports being held waiting for the test results to come through, because they've already done their full write-up, all their testing on site, and they can't issue the invoice until we provide the test results. And then again, as you know, 30-day net 30 invoice. This is the reason why we cut it in half, because I want to make sure that our clients can actually go and bill their clients as soon as they can.
Okay, thank you. And we have the next question. Does the person collecting the sample need any qualifications? Example being electric.
Technically, no, but it's very much encouraged that yes, you should know how to deal with electricity. You should really understand high voltage. We do have a sampling. We do have a sampling information form on how to do the sampling, but it's very much recommended that they're a licensed electrician who understands high voltage. Because sometimes you can sample some transformers live, others you should not, just judging by where the sample port is in relation to the bus ducts, which hold the electricity, and whether it's safe to actually get close to a 230,000 volt transformer.
Great, thank you. And our last question is, how often should we test our transformers?
Oh, that's a lovely question. Uh, Generally, it's annually. Any any industry, any company that has a transformer on site will do it annually, unless we find that there's an increase in gases, um, like a possible fault. Then we'll ask for a higher frequency. So it can be anywhere between 6 months, 3 months, 1 month, depending on the severity of the fault or how quickly the gases are generated. Because there's so much disruption from actually taking a transformer offline and checking it out internally, they tend to do a monitoring approach until they can see that it's starting to really go up. One of the biggest problems with an internal inspection is it's hard to see, because once you take the lid off, drain it down, take the lid off, and you're looking going, there's so much crammed in there that you you're mainly looking to see if there's anything right at the top that's doing it. So they tend to do a monitor approach, and if we see it start to really escalate, then you can schedule a downtime when it's good for their client and actually do the repair that's necessary, or even just bring in a spare transformer so you can take that one, the other one offline, send it into another company where they can actually take it apart and find out where the issue is.
Okay. It looks like that is all the questions for today. If you think of any questions later, we will be providing contact information in our follow up, so you can just reach out with your questions or to learn more and get started with our transformer oil testing program. I want to thank everyone for joining us today. We hope you found the information valuable and that you're leaving with a deeper understanding of how transformer oil testing plays a role in maintaining reliable electrical systems. As a reminder, this session was recorded and we'll be sending everyone a link to the webinar recording along with any relevant documents for future reference. So whether you want to revisit certain sections or share it with your team, you'll have everything you need right at your fingertips. On behalf of ALS and Stephen Durand, I want to thank you for your time and attention. We look forward to supporting you in your ongoing maintenance efforts and seeing you in the future at webinars. Have a great day, everyone.